Welcome to note set number 10. We're now going to look at how to solve circuits with periodic sources. And remember, we're saying circuits here, but in reality we're saying system, differential equation. A circuit is just a specific example of something that we can represent with a differential equation. Other systems, mechanical, other electrical systems, some including motors and things like that, all can be represented and solved this way. So we're just using the idea of a circuit as a simple case, something that you've seen before, and as EEs and COEs, probably something you're interested in learning about. So as promised and motivated earlier, the whole point of the Fourier series is to allow us to solve differential equations when the input to that system is a periodic signal. So Fourier series makes this easy. Basically, we convert the periodic signal into a sum of sinusoids, and since we're talking about an RLC circuit here, it's linear. So then we can think superposition, and superposition allows us to then treat each of the input sinusoids separately, and we will do so via phasor analysis. Again, don't be scared by the complex numbers. It's complex, but it's simple. Add up those responses and get the output signal. Now, well, periodic source, we might need infinitely many terms to do that. So we can't do it for all of them, but maybe we can do it for enough. And if we do it with a computer numerically within Matlab or something like that, then it's not tedious. So this is our idea here. So we're going to take a very practical scenario. We're going to learn how to make a power supply. This may not be the best design, but it's one that's easy to analyze here. So we've got our wall plug, goes into the wall, goes through a transformer. The purpose of the transformer is to step that 120 volts, 110 volt AC sinusoidal thing down to a lower voltage. Then we go through a full wave rectifier. You may have already encountered that in your electronics class. But if you haven't, don't worry about it. Just take my word for it as to what comes out of that. But that full wave rectifier converts this sine wave. Sine wave has a 60 hertz frequency coming out of the wall. And so what ends up showing up here as our x of t as the input to this RC circuit is this full wave rectified signal. Now, the period of the sine wave, so over here we've got a sine wave that has double this, right? And I'll draw it down here. It looks like this. So its period is this. That's 16.67. But once it gets rectified, the signal that we care about, we don't care about any of this anymore. We're just looking at this box. This thing now has half that period. So its period is 8.33 milliseconds. And you convert that into fundamental frequency, and you get something like 240 pi radians per second. So that's our fundamental frequency. And this is the circuit that we're going to analyze. So we have a periodic signal, so we think Fourier series, and we think of these ideas. Great. So here's our progression of ideas. We've got a periodic source going into an RC circuit, and we want to find out what comes out. We replace this periodic source time domain by this idea of a frequency domain view. What are the Fourier series coefficients? So we have to analyze this signal to find out what the C sub k's are. We already know what the omega sub 0 is. Then we've got individual terms. Forget about the sum for a moment and think about an individual sinusoid going through this circuit. That's easy. Figure out how it goes through using phasor analysis. So we want to take the kth phasor term of the Fourier series and use that as our input for phasor analysis. Do that for an arbitrary k. Now we know the phasor at the output. That phasor will convert back to tell us the Fourier series coefficients of the output signal. And we can do this all numerically or analytically. So let's see how to do that, assuming that we have this C sub k, which we're treating, this C sub k is the kth phasor term. That's all we have to worry about. Think back to when we were first introducing the idea of phasors. We put in something that looked like this, and we found out that this part was irrelevant. This was the phasor that we needed. So we only need to look at C sub k as a voltage source across these terminals. Now we do voltage divider. We've got our impedance of the capacitor, resistance of the resistor. Here's our voltage divider times C sub k. Very easy to do. Plug in the forms, simplify. In this case, it's easiest to multiply top and bottom by j k omega 0 c, and we get this thing. Having a little hard time drawing there. We get this this thing there. Down at the edges, it's hard to draw apparently. Let's try this one more time. We get this thing. There we go. Which multiplies the C sub k to create the phasor term at the output. Well, phasor term at the output, that's just a Fourier series coefficient for the output. So that's what we need to do. So for this scenario, we can find the C sub k analytically. There's the equation, general equation. We just have to focus on one period and put that in. But we know what that thing looks like. The original was a sine wave, so over that first part, it's still that same original sine wave. So we can put that thing in. Now we've got a rather troubling looking integral to do. We might go, what do we do? Well, we use Calc 1 ideas. Yes, there was a reason you took that course. So the best thing to do here at this point, do a change of variables, because you got all this crap here. All that crap is kind of showing up there as well. So let's do a change of variables and get all that crap out of there. So we're going to take this thing and let it be equal to tau. When we do that, changing the limits as appropriate, you have to remember how to do that, we get a simpler looking integral. Very nice. Good. Okay. And that thing shows up on the table of integrals. You do a little bit of algebra and trig, and bam, we've got our Fourier series coefficients. So we've got our C sub k's. Hey, notice that they're purely real. Could have guessed that. This thing has even symmetry. Okay, so there's our Fourier series for our x of t. We now treat each one of those C sub k's, and this is just a plot of the spectrum, so we can kind of see what it looks like. Now we can use Parseval's theorem to determine how many terms we need in our approximation for the source. So Parseval's theorem, we square our original signal, integrate over 1, again, change of variables, and we end up getting a squared over 2. Now, I'll give you a hint. The power in a sinusoid is always a squared over 2, so there's no surprise there. So that's the power of our original, and here's our approximation. We're just evaluating this for minus k up to k. We can plug in our specific results, do a little bit of simplification, and now we need to evaluate this thing numerically. We could do that in Excel, we could do it in Matlab, whatever we want to do. You look at those two ratios, a squared over 2, we've got an a squared there. The 2 doesn't cancel, the a squared cancels, the 2 combines with the 4 to give us the 8. So now we've got a form here, and we can evaluate that for different values of capital K to see what that ratio of power turns out to be. And for some reason I'm having a hard time advancing. There we go. So we evaluate this for different K values, and we can find out that for K equal to 10, this ratio ends up being like 0.9999. So we've got 99.99% of the power captured in that approximation. So that's a pretty accurate approximation. So we'll go with that. So here's our numerical approach. We're going to numerically evaluate C sub k for the minus 10 to 10 range using this formula. Then we're going to numerically convert them into the phasors. So the C sub k gets multiplied by this quantity, which we found through circuit analysis, to give us the D sub k. Then we convert the phasors at the output into the corresponding Fourier series and add up the terms. So here's our output signal. So we can find out what that thing looks like. And we're limiting ourselves to plus or minus 10. So just for some numerical specifics, we're going to pick A is equal to 10 volts, R is 100 ohms, and C is 1,000 microfarads. So here's some Matlab code to do that. This whole block here is just setting up all of our parameters. This is evaluating the form of the Fourier series coefficients. This is forming our output Fourier series coefficients by taking the thing that we just calculated and multiplying it by that multiplication factor that depends upon the circuit. So once we've done that, then we've got all of our C sub k's. Now notice that I've defined a vector of integers from, in this case, minus 10 to 10. The reason that I'm using the dot divide here is because I'm putting a vector in here, and I'm also using the dot hat. So I'm operating on vectors. It's a key part of MATLAB that makes it very, very powerful. Same kind of thing here. This is a vector of all of my Fourier series input coefficients. This thing is evaluated at all the different frequencies. So I have a vector times a vector gives me another vector. And then the rest is just like before, just summing up the different terms and then plotting them. So here's what we get. The red term is a plot of our approximate rectified sine wave, and you can see that we don't quite go all the way down to 0 there. That's part of the approximation issue. And then the green part, we see why we're talking about this as converting an AC signal into a DC signal. It's not exactly constant. There is a little bit of wiggle there, but this procedure allows us to experiment and try out different RC values to find out how they affect how much wiggle there is, or ripple, as a real engineer would say. And we can then adjust our RC value to make that as constant as we want. What we're effectively doing is getting rid of the high frequency components in that rectified sine wave and trying to leave only the DC component. Unfortunately, we leave behind some of those non-DC components, and that's what's making a ripple. Now, if we wanted to make a 5-volt DC power supply out of this, we would then clamp it at 5 with some sort of regulator, maybe a Zener diode, at 5 volts or a specific IC for voltage regulation. Then the ripple doesn't matter as long as it never dips below 5 volts. So just to illustrate, the top plot shows the C sub k magnitudes, the spectrum of the rectified sine wave, and the bottom plot shows after it goes through the RC filter, so or the RC circuit. So the RC circuit, we can see the effect of that. What happens is this thing gets multiplied by this thing to create the d sub k's. So this is the thing that's actuating this change. And if you look at the plot, a plot of this thing, magnitude versus frequency, you'll see that it has very small values in this frequency range. So what it's doing is multiplying these numbers by something very small to make them very small. And so what we're left with is one significant value at the DC level. And then these things are not zero, but they're very small, and that's what's contributing to that small amount of ripple. So that's the effect of the RC circuit. It makes all the non-DC Fourier series coefficients negligible. Now, if you get this idea into your head, it's a huge idea in lots of practical scenarios for not just making DC power supplies, but for doing lots of stuff. And we'll see this idea over and over and over, and we'll formalize this. The idea of an input spectrum gets multiplied by something, and that multiplied by something is the big idea. Gets multiplied by something that characterizes the circuit to create the spectrum of the output. Big, big idea. So here's the big idea in a picture form. We've got these coefficients. We've got these coefficients. They're linked through this multiplicative thing. This thing, h of k0, is just that expression that we had. Let's see if we can back up. This is termed to be h of k omega 0. Yes, it depends upon r and c, but you can see that it depends on k and omega 0. So for the true omega 0 value, for each k value, we're evaluating that to be something different, whatever it is. And it turns out that for this circuit, the way we've designed it, that this quantity has a small magnitude for k equal to 1, 2, 3, 4, and so on. K equal to 0, it has a value close to 1. And so that's really the big idea. And this h function, we can replace the k omega 0 and just think of it as a frequency of a function of frequency in general, is called the frequency response of the circuit. Big, big, big idea of this frequency response. So h of omega tells us how an input sinusoid gets changed in amplitude and phase as it goes through a circuit or a system. So how do we find this frequency response? Assume an arbitrary phasor x, and we'll cover this repeatedly. Try to get it here, but we'll see it over and over again. Assume an arbitrary phasor x with some arbitrary frequency omega. We're not even talking about k omega 0 anymore. This is irrespective of whether we have a periodic Fourier series kind of thing or not. Just find the frequency response of the circuit, how it responds to a sinusoid of some specific frequency, omega. We then analyze the circuit and to find the output phasor. And I guarantee you, linear circuit, it will always be something times the input phasor gives the output phasor. Always, always. There's that multiplication. Y is equal to h times x. D is equal to h times c. X is the input. C is the input. H is the system. Y is the output. D is the output. So once we've identified this h of omega, that's called the frequency response of the system, the circuit, whatever. It's the thing that multiplies the input phasor. Big, big, big idea. Thanks. See you next time.